Okay, last section of chapter 12 is about standing waves. And so a violin, a trumpet, and a clarinet all play the same note at concert A. However, they all sound different. What is the same about the sound? Are the frequencies the same? Are the wave patterns the same? And why do the instruments sound different? Okay, so what we mean by a standing wave is like if you were to take a spring and make waves in a standing wave is when the two waves are interacting with each other. There's a node at each end because the string is fixed at each end, and these are just three possibles. So let's say you have a attached end here and there's a node, so these are called nodes where there's called destructive interference, where those waves are overlapping. The amplitude, the crest and the trough are overlapping at this point, so they cancel each other out. It's called a node, and these are antinodes, where the trough and crest are the crest is overlapping with each other, and the trough is with another trough, so it's at the highest amplitude. So here's a node, 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 and there's two antinodes here. Standing waves are produced by interference as waves travel in opposite directions, and so this is happening. This can happen. I just said it with a string. If you are vibrating a spring, you can make standing waves. But also on a string, like a guitar string, you will be making standing waves. You just can't see them like this. The lowest frequency is called the fundamental frequency. This would be the fundamental frequency. This would be, and then we have what are called harmonics. So to the left is a snapshot of a single loop on that string. What would be the wavelength? Well, the wave would come from here to here, but then also down and up. So the wavelength would actually be 2L, right? So here's the wavelength, 2L. What's the frequency? Well, we know that the speed is equal to frequency times wavelength, so we rearrange that equation and the frequency would be the speed over 2L, since wavelength is 2L. So this is called the harmonic series, but this is the fundamental or first harmonic, where you have one antinode, two nodes. This is the second harmonic. The wavelength is L is going to be from this point to this point, all the way down. So this is the wavelength for the second harmonic is just 1L, because this is one wavelength. Here we have, here's one wavelength and then another half. So 2/3 L is the wavelength, and then a half of L. Here's one wavelength right here. So the wavelength is actually half of L. That's the fourth harmonic. So we can find the frequency. If you looked at this box here, we have, this is the harmonic 3F. We can find the frequency using this N as the whichever harmonic it's in, the first harmonic, second harmonic, whichever. V is the speed, and then the speed of the waves on the string over 2L is the length of the vibrating string. So N is the number of loops, or the harmonic number. V is the speed on the string. It will depend on density and the tension of the string. L is the length of the vibrating portion of the string. So how can you change the frequency or pitch on the string? So how do we change that frequency? We can change either the speed or the length of the string. So that's why with a guitar, you're pushing on the strings at different distances away from the bridge, and so you are changing the length of the string and changing the pitch.
On a given string of length L, standing waves exist only at certain wavelengths and frequencies. The lowest frequency at which a string can vibrate, called the fundamental frequency, is determined by the fact that the string is held fixed at its ends. The fundamental frequency of a vibrating string is produced by a standing wave that has a wavelength twice the length of the string, as shown here. Other standing waves that can be supported are simply integer multiples of the fundamental frequency. The sound of an instrument, such as a violin, is due to many of these frequencies being present when a note is played.
Okay, so in an air column, like a trumpet, they also cause standing waves. And some instruments, so it says flutes, trumpets, pipe organs, trombones, some instruments have pipes open at both ends while others have one end closed. So air is free to move at the open ends, so an antinode actually occurs. It's not a node there. The closed ends are nodes. So the velocity of wave is now the velocity of the sound in air because the wave is in the air, not on a string. So 25 degrees Celsius, 346 meters per second. So here would be open at both ends. Here is open at both. So you can see how we have an antinode. They don't really show the wave, but there's a node right in the middle. Antinode, node, antinode, node, antinode, and so forth. Again, it's 2L for the wavelength. Okay. Same relationship here. So for when it's both ends are open, we have that same relationship because both ends are antinodes. Okay, so now look at something that is closed on one end. One end is going to have a node right here. It's closed here, and here's going to be anode. And so this time our equation is going to be the frequency is equal to N, that's still the harmonic that you're at, V over 4L. Whoops. So you're going to use 4 times L in the denominator and with a pipe that is closed at one end. So wind instruments are not quite as simple as organ pipes because the shape is not always cylindrical. The holes change the wave patterns as well, and the size of the pipe varies along the path. So you know, like as a trumpet, it gets bigger as it gets to the bell. So let's say one string on a toy guitar is 34.5 centimeters long. What's the wavelength of the first harmonic or the fundamental wavelength? Oh, so okay, let's draw a picture. This would be, oops, the first harmonic looks like this. So from here to here is 34.5 centimeters. So what's the wavelength? You're going to multiply that by 2. So you're going to have 34.5 times 2 because the one wavelength will be here and down around. So twice that. The string is plucked and the speed of the waves on the string is 410 meters per second. What are the frequencies of the first harmonic? So I'll do the first one. So for the first one, first harmonic would be N equals 1, and then we had speed, so 410 meters per second over 2L, 34.5. And when you solve for F, you should get 590 hertz. Okay, and then you do for the N equals 2 and N equals 3. Okay, this is the use of significant figures, yes. This time a pipe is open at both ends, so you're still using the same, it's still the same equation. Okay, so we're going to have the same numbers here. And this time, though, the air temperature, so you're going to use air speed, that was 346 meters per second. So you're going to use air speed this time, but the same equation. And if the pipe is closed at one end, remember it's F is equal to NV over 4L this time if a pipe is closed at one end. So you're going to get a little different. You're going to divide all those answers by 2. So instruments do not vibrate in a single mode. Several harmonics are produced at the same time. They are just a really complex sound. And each instrument has a varied or different harmonics and intensities that are produced. So timbre is the quality of the tone resulting for the combination of harmonics. The fundamental frequency, though, determines the pitch. So you can add other harmonics will change the timbre. A tuning fork produces just a single pitch right here. Whereas the clarinet, you're going to see it is a little more jagged, and that's because there's a couple different other waves being produced, same with viola. And you can see that it's going to be a lot more complex.
Mixture of harmonics. Each musical instrument has its own characteristic mixture of harmonics at varying intensities. A tuning fork produces a pure sine wave with no harmonics. A viola string playing the same note as the tuning fork produces several harmonics, as shown in the graph. Each harmonic is itself a sine wave, and they add together to form a resultant waveform. The presence of these harmonic frequencies in the vibrating viola string produces a more complex waveform than that of the tuning fork. The difference in the two waveforms causes the tuning fork to sound different from the viola, even when both instruments are playing the same note at the same volume. Because the harmonics of musical instruments vary from instrument to instrument, every instrument has a different sound quality. This sound quality is known as timbre.
Okay, timbre instead of timbre. So beats, I don't know if any of you play the guitar, but when you tune a guitar to a piano, you're listening for beats, and this is what it's looking like in the waveform. So these waves aren't really matching up. They're off by just a little bit, and so when they superimpose themselves on each other, you get this bigger waveform, and that is going to be your beat. And so when you are, well, it's produced by two waves with the same intensity but at different frequencies, and they're just off by a little bit, and they're nearly the same, and so the sound will actually pulse. So you'll hear this loud and soft pulsing back and forth. They're used to tune instruments. So you don't want, if two instruments are tuned to each other perfectly, there would be no beats. And you get a faster beat if they're close to each other, slower beat if they're a little bit farther back. So if the tuner hears beats, the instruments are slightly out of tune. The number of beats heard per second is the difference in the two frequencies, so you can adjust it. So piano tuners that use tuning forks to tune the piano, they're listening for beats. They're trying to eliminate the beats. Or if you're tuning guitar to the piano, you listen for beats, and you want to get rid of those beats.
When two waves of slightly different frequencies are present, they can interfere. The interference pattern varies in such a way that a listener hears an alternation between loudness and softness. The variation from soft to loud and back to soft is called a beat. One beat is shown here. When the two waves are exactly out of phase, destructive interference takes place. The two waves cancel each other out, and there is little or no sound. When the two waves are exactly in phase, constructive interference takes place. The two waves add to a large wave, and there is a louder sound. As the sound continues, the waves continue to produce destructive and constructive interference, giving beats. Piano tuners use beats to tune piano strings to a reference note from a tuning fork.
Okay, so now what do you think? A violin, a trumpet, and clarinet all play the same note, concert A, however they sound different. What's the same about the sound? They all have the same pitch. The frequencies are being produced, but the wave patterns are different. And that was called timbre. Why do the instruments sound different? There's a different quality to their sound. They have different wave patterns. Okay, and that concludes chapter 12.